Hi everyone. In the previous lecture, I introduced the idea of the frequency response of differential amplifiers. We said in differential amplifiers there are four important parameters: a DM, the differential mode gain, common mode gain, a CMDM, the differential mode gain for common mode inputs, and finally we discussed CMRR. So now we are going to look at, and we said that if the impedances, because of device parasitics, capacitive device parasitics, the impedances now vary with frequency, because of which we said the gains will also start varying with frequency. Now we are going to look at how all these four parameters are going to be affected, or are they going to change as a function of frequency because of the different parasitic capacitors. So I'll start with the simplest differential pair circuit shown here. And I'm going to consider there is only one capacitance CT at the source terminal to ground. So this can be the source to bulk capacitance of these two MOSFETs and also the capacitance offered by this current source. So the CT can actually model the source to bulk parasitic capacitor of those input MOSFETs or the parasitic capacitance offered by the current source. RT is your current source resistance. Now our first step before we start analyzing the circuit is that we'll have to first draw a differential half circuit. To do that, we have to draw the circuit in such a way such that I'll be able to draw an axis of symmetry around which the circuit will be mirror image of each other. To do that, we have already seen if you have an impedance ZT of S at this terminal, we can represent it as two parallel impedances of value 2 ZTS. Now let ZT of S represent resistor RT and CT in parallel, then 2Z of T will represent a resistance of value 2RT and a capacitance of value CT by 2. So because your impedance is twice, the capacitance is half, the impedance of a capacitance is 1 by SCT. So if I want to multiply the impedance by 2, then I have to divide the capacitance value by half. So using that, what is shown here is a differential, the same differential pair drawn in such a way such that I can draw this axis of symmetry along around a line. I can draw this axis of symmetry around which the circuit is symmetric about that point or around that axis. Now what we are going to do, we'll follow the procedure and find the differential gain and common mode gain. So we are trying to study the effect of the common mode and differential gains on this due to this capacitance CT. So first, to draw the differential gain, this node will come to AC ground and this node will also be at AC ground. So the differential gain, the circuit reduces to this. Now if you see in the differential gain, the differential half circuit, we can see that there is no capacitance, so the gain will be independent of frequency. The gain is GM times R. Of course the sign is not important right now. So the gain will be GM times R. This is the magnitude of the differential mode gain and it is independent of frequency. So if you plot this as a function of frequency, it will always be constant. Now coming back to the common mode half circuit. So again, to draw the common mode half circuit, as I said, we have to open circuit this node wherever this line of symmetry cuts the circuit. We have to open circuit that. Now this is our common mode half circuit. Now this is a circuit, we have analyzed it extensively in the previous lecture. I revised it again. So I'll directly be able to write the transfer function for this circuit, which is shown here. So there is only one capacitance here, there is no load capacitance. So therefore you can expect one pole and one zero at max. We already saw the zero of the circuit can be found by using the condition when this impedance blows up to infinity. That happens when 2RT becomes equal to minus 1 by SCT by 2 and it's a left of plane 0. I'll write the magnitude of 0 in radians per second as 1 by RT-CT. And we also said we can find the pole by finding the equivalent resistance seen by this capacitance at this node. And that turns out to be 2RT in parallel with 1 by GM. And this I can approximate. So the 2RT in parallel with 1 by GM is the equivalent resistance multiplied by CT by 2 will be your pole. Again, I'll make this approximation. This RT resistance will generally be much greater than 1 by GM. So using that, I can say the pole here reduces to 2 GM by CT. So this is 1 by GM. So you get 2 GM by Ct as the pole. So that's what is shown here. The pole here is 1 plus S by omega p. So you get 1 plus S Ct upon 2 Gm. And you have a 0 written in the numerator, which is 1 plus S RTCT multiplied by the DC gain. So the DC gain for this circuit is GMR by 1 plus 2 GMRT. Okay, so because the resistance here is 2R, so that's why you get this 2 factor here. So GMR, the drain resistance, divided by 1 plus 2 GMRT is your DC gain. There is a minus sign here, but we are interested right now in the magnitude alone. So this is mod of ACM of omega or S. So now to draw this response, the Bode plot for this response, we have one pole, 1, 0. And a general rule of thumb is that if your response is flat at infinite frequencies, it usually means that the number of poles is equal to number of zeros. At infinite frequencies, if the response is flat, then the number of poles is equal to the number of zeros. In addition to that, if you don't have poles and zeros at DC, if you don't have poles and zeros at DC, then you can look at the response at DC and infinity. If both of them are flat, then we can say the number of poles is equal to the number of zeros. So first we will start with DC response, the value at DC, which will be GMR by 1 plus 2 GMRT. So 20 log of that is the DC value. And we already discussed in the last lecture, the 0 comes first, 1 by RTCT, because RT will be a much larger value, 0 comes first. This will be less than 2 GM upon CT. So CT is the same cap here, but since RT is much greater than 1 by GM, the 0 will occur first. So after the 0, the gain increases with a slope of plus 20 decibels per decade. And when it reaches a pole at 2 GM by CT, the gain starts to flatten out. The important point to understand here is that at very high frequency, even at infinite frequencies, if you see the gain is flattened out, what is the value of that gain? We discussed many approaches to find it in the last lecture itself. I can directly use that and show that this gain here, so you can assume this term is greater than 1 and this term is greater than 1, and you can also assume 2 GMRT is much greater than 1, and you can readily show this term converges to GMR. Or we can see that from this circuit at very high frequencies, the capacitance here acts like a short circuit. So this circuit simply reduces to a common source amplifier with a drain resistance of value R. So the gain of this circuit is, the magnitude of the gain is mod of A, it will simply be GMR. So this value here will be 20 log of GMR. So now we plotted ADM, which happened to be a constant for all frequencies, and ACM. So now we have both the values. We are now ready to plot ACM-DM and CMRR. ACM-DM on the other hand is simply, this is the error term which I discussed in the last class. So it will simply be some error term times ACM of S. So once you know the common mode gain, you can directly plot ACM-DM from the knowledge of the common mode gain. So the common mode gain, I'm going to take 20 log on both the sides and magnitude of them. So it will be 20 log E plus 20 log of ACM of omega. So the Bode plot or the frequency response of common mode, we are going to add a term 20 log E. So whatever graph we had here, this is the gain this is the frequency response of common mode gain. All you need to do is add plus 20 log of E. Now 20 log mod E here, since mod E is always less than 1, modulus of E is always less than 1, 20 log of this term will always be negative. So that amounts to just shifting this term. So you'll have to just shift this graph down by this value, 20 log mod E. So it will be a negative value, we'll be shifting this graph down. The pole zeros, everything will remain the same. The only difference is the graph would have shifted a little bit. So previously, the graph for common mode gain will look like this. Now this would have been shifted down by 20 log E. So finally, we have the common mode, and we also showed how ACM-DM plot looks like. Finally, we will discuss CMRR, the common mode rejection ratio. Common mode rejection ratio is given by the differential mode gain divided by the common mode gain, ACM of S, into one, of course, it's differential mode gain divided by ACM-DM. ACM-DM is simply proportional to the common mode gain times the error factor, the fractional error. So I can express in decibels the common mode gain in decibels. So here I have already assumed we have taken 20 log of cmrr, so that's in decibels, which will be 20 log ADM, the differential mode gain in decibels, minus 20 log ACM, the common mode gain in decibels, minus 20 log E. So this term here will be positive, minus 20 log E will be positive because 20 log E will be negative and minus of that will be positive. So all you need to do, if you want to plot CMRR, first plot differential mode gain, subtract it from the common mode gain and just add a fixed term. This fixed term is dependent on the fractional error. So finally, after showing these plots, I will draw the conclusions as to what is the effect of this capacitance CT on the frequency response of this amplifier. So this is the differential mode gain and this is your common mode gain. I will now represent it. So what I have shown here, CMRR in decibels is differential mode gain in decibels minus different common mode gain in decibels and some constant term 20 log of E. So here first I will plot both the graphs, both differential mode and common mode gain in the same plot, so we can directly draw the CMRR from this graph. So shown here is differential mode gain. This shown in pink here is common mode gain. So you can see that the common mode gain increases after 1 by RT CT and it starts to flatten out after 2 GM by CT. Now we have to subtract this graph minus this graph. So divisions become subtraction. So that's why we said one of the reasons why we went for logarithms is because of this. So if you subtract these two graphs, okay, so remember the difference between these two here, this point, so when we are subtracting the two graphs, you have to think that you are dividing the absolute values. So GMR divided by GMR by 1 plus 2 GMRT, this is what we are doing. So this value is given by 1 plus 2 GMRT. This is the ratio of ADM by ACM. So that's what I've written, 20 log of, but on a decibel scale, this gap here will be 20 log of 1 plus 2 GMRT. Okay, and E, there is also a constant term E here. So maybe I can show that E line along this. So this will be minus 20 log E. Or I can write it as plus 20 log E. I can subtract that again. So first I'll show you the profile of CMRR. After that we have to just add the term 20 log E. To understand the profile, how the frequency variation looks like in a CMRR, you'll have to just subtract ADM minus ACM. If you subtract this, so this peak value here will be 20 log of mod of 1 plus 2 GMRT. To this we have to add minus 20 log of mod E. So we get this term. Then since your ACM is increasing with frequency, CMRR will decrease because you are subtracting the two. This will decrease with a slope of minus 20 decibels per decade. It will keep decreasing till we reach the pole 2 GM by CT. After that, if you see, both ACM is equal to ADM. So the difference in decibels will be 0 dB. ACM plus ACM, ADM minus ACM will be 0 decibels. Plus, you'll have to add this term, this constant factor, which is minus of 20 log E. So the flat value here will simply be equal to minus of 20 log E. So remember, higher the CMRR, the better the system is. Ideally, CMRR should be equal to infinity. Higher the CMRR, the better the system is. Okay, so now we have plotted all the responses. Now we'll try to interpret these results. What is this analysis telling us is that if you look at this differential circuit, here, or the circuit which we began with in our analysis, what we see from this circuit is that this capacitance CT, so that is source to bulk capacitance or the capacitance, parasitic capacitance due to the current source, has no effect on the differential mode gain. Because that happens to be a differential ground here, this node. So the voltage, AC voltage across the capacitance is 0. So the capacitance contributes it has no contribution to the differential mode response. However, the common mode gain has a very strong dependence on the capacitance CT. We saw that, if you recall this analysis which we carried out here, initially the common mode gain was very small, which was GMR, but it was getting divided by 1 plus 2 GMRT. 2 GMRT is a very large number. It was very small because generally RT is a very large number. It will be generally much larger than R. So therefore, we were seeing that the common mode gain was very small. But as frequency increases, as frequency was increasing, we saw that the common mode gain was also increasing. It increases and finally it reaches a maximum value of cmrr. At this frequency, at very high frequencies, which is after the pole frequency 2 gm by ct, the common mode gain became equal to the differential mode gain itself. If you recall our discussions on current bias differential pairs, we said one of the most important properties of a current bias differential pair is that it can reject common mode signals. Its common mode gain was negligibly small. But what we are seeing now is that because of this capacitance CT, because of a parasitic capacitance CT, the common mode gain is now becoming equal to or is becoming as high as, it's becoming, because of this parasitic capacitance CT, it's becoming as high as the differential gain itself. So that's what we are concluding from this analysis, that the common mode gain is becoming as high as the differential mode gain itself. So that's the effect the parasitic capacitance CT has on the frequency response of the differential pair. CMRR is just a reflection of, how poor the common mode gain or how good the differential mode gain is and how poor the common mode gain is. So that's what, if you see here, at high frequencies, as frequencies increase, you can see that since ACM has increased, CMRR has decreased. Okay, so it's a reflection of how poorly you can reject differential mode signals or common mode signals. Okay, CMRR is a quantity that tells you how well you can reject common mode signals. If it is very high, it means you can reject common mode signals very well. The circuit can reject common mode signals very well. But what we are seeing here is that CMRR was very high at low frequencies, but at very high frequencies, CMRR becomes very low. This is the point where the common mode gain becomes equal to differential mode gain. That's why your CMRR is decreasing, because even though differential mode gain is remaining the same, but common mode gain is increasing, so CMRR is decreasing. Okay, so you can directly see CMRR depends on ADM by ACM. So for CMRR to decrease, either ADM should decrease or ACM should increase. Both these possibilities will lead to a decreased CMRR. And a decreased or low CMRR is definitely a bad thing, because a differential amplifier, CMRR is a defining metric which tells us how good or how symmetric the differential amplifier is, how well it can reject common mode signals. The whole idea of going for differential amplifiers is that you are now operating differentially using differential signals, and therefore you should not, in theory, respond to common mode signals. So now we will take another circuit. What we have done here is we have introduced two parasitic capacitance at the drain terminal. Now these capacitors can be the drain to bulk capacitances, parasitic capacitance of these two MOSFETs, or it can be some parasitic capacitance associated with the resistors. Resistors also give some parasitic capacitance in an actual layout. Once you draw the layout and extract the circuit, resistors will also have some finite parasitic capacitors. Or these capacitors can be the next stage. This differential amplifier can be driving another differential amplifier, and these capacitances can be capacitive loads from the next stage. Now we will see what effect does this capacitance, in addition to the capacitance CT here, what effect does this capacitors have on the frequency response of this differential pair. Again, we start with drawing the differential half circuit. So we have split this resistor RT-CT as 2RT and CT by 2. So this impedance is 2ZT. Now we are going to first draw the half circuits. So for differential mode, this node will come to AC ground. In a differential mode analysis, for a differential mode operation, this node will come to AC ground. So that's why we called it as differential ground, to distinguish it from the conventional AC ground. Okay, only if you apply differential signals, this node will come to AC ground. So that's why we call it differential ground. So the circuit for this, the differential half circuit, reduces to something like this. Okay, so at the output you still have a capacitance R and C. So you have a load resistance which is a parallel combination of resistor and capacitor. And for the common mode half circuit, to draw a common mode half circuit, we discussed that we have to open circuit this node and this becomes your common mode half circuit. So that's what I've shown here. So this is the common mode half circuit and this is your differential half circuit. So this is a very standard common source amplifier with a resistor and capacitor load. So of course you can derive this from starting from fundamental principles, but by now we are at a point where we can directly write the gain expression for this. We know there is a pole at 1 by RC. Directly we can see that. Okay, and the transfer function, the DC gain is GM times R multiplied by 1 plus SRC will be your transfer function for this. Okay, you can simply multiply GM times Z of S, and Z here is R parallel 1 by SC. So R parallel 1 by SC is nothing but R by 1 plus SRC. So that's what we get here. But as I said, at this stage these results should be very obvious by now. So this is the expression for ADM of S. So ADM of S is a single pole response. It has one pole and one low frequency pole and no zeros in the system. Okay, one pole at 1 by RC and no zeros in the system. Now on the other hand, for a common mode half circuit you have two capacitors, and we have already analyzed this circuit. We saw a circuit like this has two poles and one zero. The zero is given when this impedance blows up to infinity, so that will be 1 by RTCT. So that's what is shown here. And the pole for the circuit, there are two poles. One pole is at the output whose value is given by 1 by RC. The other pole is at this node whose value is given by 1 by CT by 2 into 2 RT in parallel with 1 by GM. So I have already derived this, so I am not going to spend time on this. So I assume you know that. So this pole is given by this, and approximately we assumed 2 RT is much greater than 1 by GM, so this pole reduces to 2 GM by CT. So 1 by RC, 2 GM by CT are two poles, and the 0 is at 1 by RTCT. And DC gain for this circuit is GMR by 1 plus 2 GMRT. We know the DC gain and we know the poles and zeros, so we can directly write the transfer function. So we have 1 plus S RTCT here, that's the 0, and two poles at 1 plus SRC and 1 plus SCT by 2 GM. So this is the pole due to the short circuit transconductance. This is the pole due to the output impedance. Now once we have both these gains, the differential mode gain and the common mode gain, we will start drawing its Bode plots. For differential mode gain, the gain is given by GMR by 1 plus SRC. So it's a single pole system. DC gain is, when I plot Bode plot for this, DC gain will be 20 log of GMR. And after 1 by RC, once it encounters the pole 1 by RC, the gain starts decreasing at the slope with a slope of minus 20 decibels per decade. Eventually at infinite frequencies it goes to 0 or minus infinity decibels. That should make intuitive sense because your output capacitance will start shunting out the resistance, and eventually at infinity the capacitance will act like a short circuit. At infinite frequency the capacitance will act like a short circuit and the voltage gain will be 0 or minus infinity decibels. Now to plot the common mode response, we will again make this assumption: 0 comes first, RTCT is so small, 0 comes first, followed by the pole due to this, the capacitance CT by 2, so it will be 2 GM by CT, and after this we are going to encounter 1 by RC. So this is the order in which the zeros and poles are going to appear. You will encounter 0 first, the first pole next, and the second pole later. So to plot the response, the common mode gain starts with GM by 1 plus 2 GMRT, 20 log of this term, and once you encounter 0, that is this term, the gain starts increasing with a slope of plus 20 decibels per decade. After the first pole, once you encounter the first pole, the gain starts to flatten out. We already discussed what will be this value. This value will be GM times R. The peak value it reaches if this pole comes first. 2 GM by CT comes first, so this will be GMR. So this will be 20 log of mod of GMR. And after 1 by RC, the common mode gain is decreasing. Now let's look at the common mode gain plot and try to infer what effect does these capacitors have. We saw that because of CT, common mode gain starts increasing because CT starts shunting out 2RT. So if you see here, 2RT is introducing some kind of resistive source degeneration. Source degeneration reduces the transconductance by a factor of Gm by 1 plus 2 cmrr. So this is a result we have discussed long back when we were talking about source degeneration in MOS amplifiers. We said by adding a resistance to the source terminal, you will be reducing your transconductance by a factor of 1 plus 2 cmrr. But what happens is that this capacitor, after a frequency 1 by Ct RT, starts shunting out this resistance, which means it's reducing the net source impedance. At the source terminal, the resistance at DC was 2 RT to ground, but now it's going to reduce further and further because of the presence of Ct, and at some point it's going to look like a short circuit, and at that point your gain will become GMR. So that's what I've shown here as GMR. After this, the output capacitance will start shunting out the output voltage. So at that point your output voltage will start decreasing. So that's what we are seeing in this gain as well. The gain starts decreasing. Eventually at infinite frequencies, the output capacitance will go to 0. At that point, the gain of this circuit will also become negligibly small. Okay, it will go to nearly 0. So what we see here is that the common mode gain is increasing, which is not really a good thing, and it's becoming maximum here at this frequency, in this frequency range between 2 Gm by Ct and 1 by Rc. It's becoming equal to the differential mode gain itself. So that's really not a good thing. We said the current bias amplifiers, the main advantage is a very low common mode gain, but now common mode gain has become equal to differential mode gain here. But an interesting thing to notice here is that the common mode gain is decreasing after 1 by Rc. We said a lower common mode gain is always good, and here we are noticing that the common mode gain is decreasing at very high frequencies. So does this mean that it's a good, at very high frequencies the circuit is performing better? So we'll see that answer, it's not really the case, and we'll see why is it not. So now we have differential mode gain and common mode gain. Using this knowledge, I'll try to plot the CMRR, the graph of CMRR. The graph of ACM-DM is just a shifted version of this graph, so I'm not plotting ACM-DM. So I'm directly going to plot CMRR. So to plot CMRR, I've plotted a DM of S and a CM of S together on the same graph. Shown in pink is ACM and shown in yellow here is ADM. So you can see here, after this frequency, after 2 Gm by Ct, both the common mode and differential mode gain becomes same. They both become GMR. So that's why it's indistinguishable. And after that, at 1 by Rc, both the gains are going to roll off with a slope of minus 20 decibels per decade. Now, what I'll do is to show the plot, I'll just subtract ADM minus ACM. So this gap here between ADM and ACM will be 20 log of mod of 1 plus 2 Gm RT. So it's the ratio of ADM by AGM in the absolute values. On a log scale, you get this. So subtract the two. So at DC, you are going to get 20 log of this term minus 20 log of E. So this is a positive term. We are adding some positive term to it. Now if you see here, this difference is decreasing. So CMRR is this, what CMRR tells you is the difference between ADM and ACM. Since the difference is decreasing, CMRR will also decrease. So the larger the difference, the greater the CMRR. So CMRR is decreasing. So, or you can also say that this is a 0 for ACM. For ACM, this is a 0. So for CMRR, it will act like a pole. So that's what we are seeing here. The CMRR is decreasing. Because your common mode gain is increasing, CMRR is decreasing. At one point, after this frequency 2 Gm by Ct, common mode gain becomes equal to differential mode gain. At that point, the difference between ACM and ADM is 0, and this value will simply be equal to minus of 20 log of E. So your CMRR is ADM in decibels minus ACM in decibels minus 20 log of E. So this value, when these two become equal to 0 decibels, you will be left with minus of 20 log E. It's going to remain flat till we encounter 1 by RC. Now if you see here, of course the ACM is decreasing at high frequencies, but you should notice even 8DM is decreasing. 8DM is also decreasing at very high frequencies. So therefore, the difference between the two will still be 0. Difference between ACM and ADM will be 0. Therefore, the gain will remain constant. The CMRR will remain constant and it will be equal to minus of 20 log E. So what we are noticing, the effect of this output capacitance C is that it has an effect on ADM. The differential mode gain starts decreasing after, because we have a pole is introduced in the differential mode gain transfer function. So differential mode gain starts decreasing at very high frequencies. So that's what we saw because of this capacitance. CT anyways had no effect on the differential gain. We also noticed that the common mode gain, ACM of S, was also decreasing at higher frequencies, shown in the pink graph here. ACM was also previously, when we did not have the output capacitance, the common mode gain was just a constant. But now ACM, the common mode gain, starts decreasing at high frequencies. The most important thing to notice here is that even though we introduced the capacitance here, even though we added a capacitance here, this pole, the pole formed by the output capacitance, has no impact on the CMRR. The common mode rejection ratio is independent of this load capacitance. And that makes intuitive sense because of this output capacitance, you are going to get a pole in ADM. You are going to get the pole in ADM. You will get the same pole in ACM as well, because you are taking the output at the same terminal. This capacitance is with respect to ground. So you will get the same pole in ACM as well. In this circuit, you will get the same pole. Therefore, both the poles will cancel out. When we measure CMRR, CMRR is the ratio of ACM by DM by E times ACM of S. So the poles in both, if they both are same, they will get cancelled out. So that's why you don't see any effect of the capacitance C on CMRR. ACM and ADM both changed, but the change in both of them was very similar because of this capacitance, and that is why you don't see any change in the CMRR. CMRR remains constant. Now finally, I am going to analyze another circuit wherein the capacitance C is not at the output terminal, but now it's going to be between the two terminals. So this is called a differential capacitance. It's a capacitance between these two nodes. So we don't have a capacitance to ground, but rather a differential capacitance between these two nodes. Now we will see the effect of this differential capacitance on all the gains, the common mode gain, differential mode gain, and CMRR. We already saw the effect of the single-ended capacitances. So if I'm adding two capacitors on these two sides, we saw what effect these two capacitors have. We saw that it has no effect on CMRR. The differential mode gain decreases and common mode gain also decreases at very high frequencies, but they had no effect on CMRR. So first step, to draw the differential half circuit. So this impedance capacitance, the impedance offered by a capacitance is 1 by SC. So I'm going to split this impedance into two halves. So each of value 1 by SC, half SC, and this will also be half SC. So I can model this as a capacitance of value 2C. So I can split a single capacitor of value C into two capacitors of value 2C and 2C connected in series. So that's what I've shown here. So along this axis of symmetry, I'm first going to draw the axis of symmetry, and then first we'll draw the differential half circuit. This node will come to AC ground and this node will come to AC ground. So the differential half circuit reduces to this. Again, CT has no effect on the differential half circuit. Okay, so only the capacitance C, the differential capacitance, has an impact. Now if you see, it reduced to a very similar circuit which we encountered in the previous problem, but now the pole will be at 1 by 2 RC. That's the only difference. So the differential mode gain response is shown here. DC gain is 20 log GMR for the circuit, and the pole occurs at 1 by 2 RC, and after that the gain decreases with a slope of minus 20 decibels per decade. Now we'll draw the common mode half circuit. To draw the common mode half circuit, so again I have these two capacitors here. I need to open circuit these 2 points. The moment I open circuit this differential capacitance carries no current. So because the differential capacitance carries no current, because this node is open here, the voltage drop across it will be 0, and these two capacitors will not appear in the common mode half circuit. So that's something to note here. If I have a differential capacitance between these two nodes, that will have no impact on the common mode response. Okay, if I have a purely differential capacitance between the two terminals, it will have no impact on the common mode response. So now this is a circuit we have already, it's a done and dusted circuit, we have already analyzed this, I've shown here. So we can directly write the poles and zeros. Since there is no capacitance here and there is only capacitance here, we can directly see that there will be one pole, 1 0. I have already analyzed this circuit in the beginning of the lecture. For the first circuit, when we took it without any capacitance at the output terminal, we got a similar circuit. I'll directly code those results here. So you will get a 0 at 1 by RTCT. DC gain will be GMR by 1 plus 2 GMRT, and pole will approximately be at 2 GM by CT. So you will get 1 plus 2 GM by CT. So now we will draw, there is a minus sign here, but at this point we don't care about the signs here. So the gain plot will look like this. The DC gain starts at 20 log of mod of GMR by 2 GMRT. After the 0, the capacitance will start shunting out the source resistance. So which means the gain will start increasing. So the capacitance is reducing the net impedance of the source terminal, which means the gain will start increasing. So as the gain increases, eventually after the pole GM by 2 GM by CT, so we get 2 GM by CT, the gain flattens out and it reaches a peak value of GMR. So this is the DC gain of the amplifier. So it reaches a peak value of GMR. Okay, sorry, this is the differential gain of this amplifier. So we said the common mode gain increases and it reaches the differential gain itself. Now with the knowledge of this, we'll quickly plot CMRR. I've shown both differential mode gain and common mode gain. Differential mode gain starts decreasing after 1 by 2 RC. Common mode gain reaches a peak value of GMR and it stays constant. So this is the graph. So we have a 0 here at 1 by RTCT. The first pole 2 GM by CT, and the pole in the differential path, this pole doesn't appear in common mode half circuit. So that's given by 1 by 2 RC. So from this I'll draw this CMRR plot. So this difference here is 20 log of 1 plus mod of 1 plus 2 GM RT. So if I plot this, it's going to, the CMRR is going to be flat here. This value here is going to be 20 log of 1 plus 2 GM RT minus 20 log of E. So you have to subtract these two plots and add this term minus 20 log E, 20 log of mod E. Okay, that's the peak value. As soon as we encounter the 0, common mode gain starts increasing. So CMRR will decrease and it reaches 2 GM by CT. At that point, ACM becomes equal to ADM. So difference between ACM and ADM is 0. So this value will just be minus of 20 log of mod E. It will remain constant till 1 by 2 RC. After 1 by 2 RC, if you see this graph, common mode gain is remaining the same. ACM is remaining the same, but ADM is decreasing. So we said CMRR is ADM by ACM. So if ADM is decreasing, CMRR will also decrease. So therefore, your CMRR is going to decrease at high frequencies. So that's what this analysis is telling us, that the CMRR is degrading significantly at high frequencies because your common mode gain is remaining the same, but differential mode gain is decreasing. Okay, so that is why, because your CMRR is getting poorer and poorer, after a point at very high frequencies, common mode signals will start dominating in your amplifier output in the presence of mismatches, and it will even at high frequencies, it will dwarf the differential signals itself. So I told you, remember CMRR like some kind of a signal gain by noise gain. Noise gain is remaining the same, but signal gain is decreasing. So which means at some point noise will start, the common mode noise will start dominating the circuit. Okay, that's what this graph is telling us. A poor CMRR means that the common mode behavior is not good enough. Common mode response is good, but I mean the amplifier is not able to reject common mode signals well enough. Okay, so we have analyzed three different circuits. I'll stop at this point. We'll consider a few more examples in the upcoming lectures. Thank you.